In today's repetition course, we will have a look at an acidic catalyzed isomerization of olefins. This olefin can migrate along that ring until it reaches a position where the olefin is 3 times substituted. As we know, this is, well, energetically favored compared to the structures where the olefin is only substituted twice by alkyl groups. And as I said, under acidic catalysis, this reaction is possible. And now we will have a look at the mechanism. So, acidic catalysis means the starting material, structure 1, is protonated. If it is protonated at this position, then this carbenium, an ion, will be formed as a reactive intermediate. Let's call it reactive intermediate R1. So from here, we can only deprotonate either here or at this methylene group. It doesn't matter, it goes back to this structure, to the starting material. That means this reaction pathway to this carbenium ion is a dead end. On the other hand, if we protonate here, then we have a carbenium ion here. And then it can either react again to the original structure 1, but it could be also deprotonated here. Then we have that olefin number 2, where the olefinic moiety has already migrated 1 position further. Again, now protonating here, then the carbenium ion, cation, will be located here, and deprotonating at the tertiary position, then we have the olefin that is already 3 times substituted. Of course, this can also be protonated again here at this position. Then we have a rather stable tertiary cation. However, again, this is some kind of dead end pathway, because preferentially it will be deprotonated either here or there. This goes back to that olefin. If we deprotonate here at that CH3 group, then, okay, in equilibrium it might be formed the product with the exocyclic double bond, but this is clearly energetically disfavored compared to that one. So let us construct now the diagram of energy and reaction pathway. First of all, we should compare the energy level of these 3 olefins. As I said initially, this one, the 3 times substituted, is energetically favored compared to the 2 times substituted. So the energy level of 1 should be clearly above the energy level of 3. What about the energy level of structure 2? Well, the double bond has migrated to the next position, and therefore the CH3 group has a bit less demanding, sterically less demanding surrounding. It has still that CH2 group, but on that side we have changed from a CH2 group to a CH group, less sterically demanding, therefore a little bit favored energetically compared with 1. So this one a little bit further down. Okay, let us compare the reactive intermediates, those carbocations. The reactive intermediate where the carbocation is located closely to the methyl group here, is inductively best stabilized compared to the others. So, from R1 to R2 to R3 and to R4, we go energetically a little bit downhill. From R3 to R4, it is rather distinct step, because here it's the first time where we have a 3 times substituted carbenium ion. This is the tertiary carbenium ion is clearly the most stable one. So this is a solution to our problem. However, we should keep in mind that also 1,2 hydrogen shifts can occur, closely related to Wagner-Meerwein rearrangement. That means from, for instance, R2 to R3, also directly the isomerization can occur when one hydrogen here is migrating, carrying the electron, the bonding electron, with him. So that means we have a transition state where that cation is bound, is coordinated to that olefin and is bound equally loose to this and that position. As I said, this is just a transition state. And this means, well, between all those reactive intermediates, such a transition could occur. So, in that case, we would assume we start here, we protonate, and then we go from here to that one, and this is then deprotonated to the final product 3. So, which pathway is preferred? Well, I think we don't know. All pathways can happen here. You are certainly on the right side if you say, well, this could happen, that could happen, also a mixture of both. Thanks for listening.